assignments happened, I think.
Well, if you have worked
so with, welcome back, everyone.
Once you have worked and learned how to pronounce Ising Mroczek, then
yes, thank you. I appreciate it. Okay, so I welcome everyone back from our very brief break. I'm going to switch gears a little bit here. We had a lot of hydro today. So I wanted to start with a discussion of the QCD phase diagram and more recent experimental efforts and the direction of mapping the QCD phase diagram, just because I think it's important. I know everyone has seen it many, many times, but I think it's important still for context. Then I'm going to start discussing the work pertaining to this talk, which is how my collaborators and I constructed a family of equations of state with a critical point for QCD. And then more recently, how we took that construction that we developed a couple years ago and enforced some the correct charge conservation constraints for heavy ion collisions. And then lastly, I'm just going to discuss what that implies in terms of actual heavy ion collision experiments. Okay, so the QCD phase diagram, we love it, but we don't know very much about it. I'm sure at this point you've heard many times that we only have high precision results vanishing baryon chemical potential, where it is possible to perform first principle lattice calculations. Other than that, we're kind of in the dark here, and that is because QCD suffers from the sign problem at finite densities. The problem is QCD is very interesting, and we have all of this rich physics across different regimes. So anything spanning from the early universe, a hadron gas to neutron star mergers, all of that should be described by QCD. So this is certainly a problem that is very interesting to different communities in physics. To my talk here today, the main question is, what exactly are we probing in terms of the QCD phase diagram in low beam energy heavy ion collisions and also fixed target experiments even? So as you might know, as you increase collision energy, you're actually decreasing baryon chemical potential. So as we lower collision energy, we go towards higher density regimes. So in terms of this phase diagram that I'm showing here, I know it's quite busy, but I think it describes all the features that we need here. The first one being the chiral transition line from lattice, which is this red band over here. So these are results from lattice in terms of a Taylor expansion about mu b equals 0. And then we have, just for context, what we think our experiments are probing. So we have LHC here, higher energy collisions, and then we have RIC, and then the beam energy scan program, of course, RIC is probing higher densities. And then also, in terms of multi-messenger astrophysics, we have neutron star mergers and solitary neutron stars. And we think they might probe a first order phase transition. The two lines you're seeing here, the top one corresponds to the QCD first order transition. So this would be the QCD critical point. And then the lower one, this tiny one, is just a liquid gas phase transition, which we can describe with just the van der Waals model. So the point is, now that we are moving towards these higher densities, what happens when we run into a more complicated description that we haven't developed yet? What happens if we run into a critical point? The fact that we don't have the answers for this, of course, poses enormous challenges for interpreting experimental results. So as a community, what is currently on our to-do list? It's a lot. So thinking about the entire evolution of a heavy ion collision, we don't have a description for initial conditions and early dynamics in terms of critical effects. We also need to incorporate it into the subsequent hydro evolution, and then of course, the hadronic freeze out and hadronic transport, and also out of equilibrium effects. We don't even know that the system that we're dealing with is fully equilibrated, and Travis discussed that last Wednesday, if you want to go back and have a look at his slides. That's not to say that there have not been efforts in this direction. Certainly many people are working on this. There are more works than I could possibly fit in the slide on this topic, but we're still quite far from where we need to be in terms of making direct theory to experiment comparisons. And of course, all of these components require an equation of state as an input. And when we're talking about a critical point, this equation of state must satisfy a couple things. The first one is that we need a critical point in the correct universality class. And the second thing is that that equation of state needs to match what we already know from lattice QCDs. So including a critical point should not mess with the description that we have already figured out. And this can be done in a couple of different ways. You can think about that 2D phase diagram, that expansion in terms of that expression about mu b equals 0, considering that you have no strangeness and no electric charge chemical potentials, or you can impose certain charge constraints. For heavy ion collisions, the relevant ones would be strangeness neutrality, because there's no initial strangeness, and due to the timescales of the system, there's no time for strangeness to be produced. Your final state should not contain any strangeness because it wasn't there to begin with. We also need, just from the particles that we have initially, this electric charge to baryon density ratio to be respected. And the first scheme we developed in this work that was published in 2020, and then we recently modified it to include charge conservation constraints. And that's what I'm going to be discussing from here on, so you can assume strangeness neutrality starting from now. So the outline that we first developed has many components. So I'm going to sort of go through this recipe of how to produce this equation of state with the critical point that matches our requirements. The first thing is that you need to find a critical point somewhere. We don't have a critical point in QCD. We have no idea what it looks like. So we need to borrow it from a different theory. And that, of course, will introduce a new set of variables that you have to deal with. But you want the QCD phase diagram. So you need to map and match these new variables to QCD ones somehow. And that would introduce some free parameters that come from this mapping. Then we can certainly use whatever information we have from lattice QCD to reduce the number of free parameters. And at this point, you have a complete description of your system. From there, you can then develop your Taylor expansion, you calculate your coefficients, and you can reconstruct the full pressure from this Taylor expansion. The last step is sort of triviality, is just we need to make sure that we are applying things to the regime where they apply, and at lower temperatures, we know that the system can be well described by a hadron resonance gas, so we have to do that merging. And then once you have all that, you can obtain all your thermodynamics from your pressure. So now I'm just kind of going to go qualitatively through the steps of the calculation. I'm not going to bother with the many details of the calculation. I'm just going to sort of point out the different components. So our critical point comes from the 3D Ising model, and that is because QCD is expected to be in the same universality class as the 3D Ising model. So we are essentially borrowing this phase diagram, this critical region, from the Ising phase diagram. And that, of course, is already not trivial. There is not currently an analytical solution to 3D Ising model. So that requires us to use a non-universal parameterization, so introducing more variables. But that doesn't matter because that description already exists and we can just implement it. It's just an additional computational step that has to be taken. Then once that's done, we need to figure out how to map this phase diagram with our critical point of interest to the QCD phase diagram. And because we don't know the size and shape of the critical region in QCD, there are unknown features, we have the choice for how we do this mapping. And our group in particular has chosen to use a linear map. This is not by any means a choice that is motivated by first principles. It's just the simplest choice we can make. So there is certainly freedom there to explore different maps. But with the linear map, you introduce 6 parameters that are 2 that are related to the position of a critical point on the QCD phase diagram, which I show here in red. There are 2 angular parameters which correspond to first how you rotate your Ising phase diagram with respect to lines of constant t. And then you can also rotate your Ising axes with respect to each other. So instead of having orthogonal axes, you could have something else that's also not limited by any physics. And then you have 2 scaling parameters, one that is global. So that would be kind of like making the entire phase diagram bigger or smaller. And then there's a relative scaling parameter, which can kind of like squish it around and reshape it. So with 1 and 2 combined, we now have a critical point in the correct universality class, so we can check that off. And now we're working with QCD variables, so we can move forward. Then the next thing we can do is use information from lattice to reduce the number of free parameters in our model. And at this point, phenomenologically, it is a safe assumption to say that the transition line follows the parabola with curvature kappa. So the transition temperature follows this equation I'm showing here. And I would just like to point out that in the literature right now, as far as I'm aware, the 4th order term is consistent with 0 in the regime where we have lattice calculations that apply. And there are several calculations for the 2nd order term, this kappa, and they're largely consistent with an error. So we make a choice to use the value from our collaborators. But once again, there is freedom here. And so that gets rid of, so once you fix the other 4 parameters, you get your transition, your critical temperature, and also alpha 1 just from the geometry of the parabola. So we reduce the number of parameters from 6 to 4, which is good. You always want to reduce your number of free parameters. The other 4 parameters, I should point out, there's no physics motivation that we can use to say anything about them, so they are largely free at this point. Okay, so at this point, you can build your Taylor expansion, and the typical way to do this is just to Taylor expand the pressure around mu equals 0. And the coefficients of this Taylor expansion are proportional to the susceptibilities, which are simply the derivatives of the pressure with respect to the baryon chemical potential. And these are available directly from lattice calculations. And in our case, we also have to get them from the 3D Ising model. And then we have to do this sort of construction where we combine the two, but I'll get to that in a second. So the first thing to note is that we have lattice data available, and in the low temperature regime, also at vanishing barrier density, we can match it to HRG. So we can parameterize those curves for the susceptibilities, and we have our coefficients for the lattice, for the Taylor expansion. And so what I'm showing here right now is just the results and the data that we use for the 2nd and 4th order coefficients. Our procedure only goes up to 4th order in this Taylor expansion. There are lattice results for higher order coefficients, but at this time, we have not been able to implement them in our calculation just because with this Ising mapping, there's a lot that happens and those terms become very expensive to compute. So at this point, our calculation is cut off at 4th order. I'm also showing here that this is when you can start enforcing or not the charge density constraints. So I'm showing both what this coefficients would look like or what the susceptibilities look like when you enforce Strangeness neutrality versus when you assume US and UQ are 0. Now, just going back to that point of the coefficients, you can see here that the coefficients we obtain from lattice, so the data that we have from first principles, is what we assume to be the true coefficient. And that true coefficient is a sum of a contribution from our Ising computation versus the non-Ising one. So because we have lattice and Ising available, it's just a simple subtraction to get the non-Ising contribution. And this is sort of what it looks like qualitatively. This step here is what I mentioned before, is just something you have to be careful with. At lower T, a hadron resonance gas is a suitable description of the system. And we do this merging smoothly via a hyperbolic tangent switching function, which I'm showing here on the left. And just an important note here is whatever charge constraints you choose to impose or not, they must be consistent because these pressures are going to be computed separately. So there is a pressure that comes out from our procedure, and then the pressure you compute with an HRG model. They must carry the same charge conservation constraints. And at this point, you have your pressure, and that's fantastic. You're done. Exactly what we wanted. And then for the thermodynamics, which is the fun stuff, you can get pretty much whatever you need from derivatives of the pressure and thermodynamic relations. So just to show an example of what this critical region would do to the phase diagram, or to the thermodynamics of the system. If you look at, for instance, the entropy density, you can see that the entropy density and other first order derivatives display a kink near the critical point. And then if you go to higher order derivatives, this effect is enhanced, of course. And I'm showing here the speed of sound, which is an input to hydro simulations. So this just goes to show how important it is to include a critical point in our computations, because clearly there's a lot going on in that critical region. And I'm going to add an extra step here. We haven't published on this yet, but this is something we are looking into very actively right now, which is to explore our parameter space. So since we, just going back to that point, have some free parameters that were introduced in that mapping from Ising to QCD, thermodynamic stability is not guaranteed. So we can't just do whatever we want with those free parameters. Yes, they're largely free, but within what statistical mechanics allows you to do in terms of stability and causality. So one example here in our first paper, an exercise we did was to fix the critical point and also the angle of the Ising axes, and then change the scaling parameters. So essentially what we're doing here is changing the size and shape of the critical region. And you can see that that in itself could drive your choice of parameters, your equation of state to be stable or unstable. So each point on this plot is a choice of parameters and an equation of state, and then we characterize that equation of state as being stable or unstable. And you can see that certain choices are no good. And this, of course, as I said, imposes constraints on the size and shape of the critical region, which is especially important for experimental searches of the critical point, which is happening right now. For instance, the beam energy scan of the second beam energy scan program. The results I'm showing here are star results. So lots of collaborations are looking into what we should expect to see in terms of net proton moments, especially the higher moments, which diverge with higher powers of the correlation length. So at the critical point, the correlation length diverges. If you're near the critical point, maybe you can start to see some critical effects by looking at these higher order moments. So it is extremely important that we, on the theory side, account for critical effects when we're making these analyses and comparisons. So now just going back to the equation of state side of things and our work on it specifically, the role of strangeness neutrality is quite important. So just beginning with the pressure itself, there is a larger difference that arises at higher chemical potentials, which is exactly the regime that we are very interested in. And that's expected, I should point out. We know why that happens. It's just due to the relationship between those different charge densities and how those charges are conserved. And then we can look, for instance, at certain derivatives. So barium density would be a first order derivative. And there's a huge difference at high temperature because when you, and also I should point out here in case it's not clear from the plot, this equation of state difference that we're looking at is enforcing strangeness neutrality versus not enforcing strangeness neutrality. So with that being said, if you remember those plots for the susceptibilities I showed, they converge to different values. So this accounts for this very large difference that we see here in high temperature. Another thing we can look at is isentropic paths. So these are paths probed by the system in the absence of dissipation. So if you were to just run a diohydro on top of this, these would be the paths that you would be probing with your system. On the left, I'm showing a bunch of different isentropes. And on the right, I'm showing the comparison between when you enforce strangeness neutrality versus when you do not. And you can see that this changes quite a bit, which region specifically of the phase diagram you're probing with your system. So safe to say that strangeness neutrality plays an important role here. And I am very sorry. I know no one's going to complain because it's the last session. It's going to be long. But if you haven't noticed, my voice is not doing great. I am in Texas and they like AC a lot. So I didn't want to push this talk too far just because I'm scared I'm going to lose my voice. So I'm just going to wrap everything up. I'm sure people are not going to have a problem with this talk being a little shorter. So I just want to outline what our procedure guarantees and what it doesn't, and what it means for the field and what's still left to be done. So our procedure guarantees that strangeness neutrality and fixed baryon number to electric charge ratio and the correct ratio are enforced in your equation of state, and it matches lattice QCD at mu equals 0. And it also contains a critical point in the correct universality class. It's also ready to be implemented in hydro calculations whenever the hydro framework is ready to run with critical fluctuations. The equation of state is waiting for you guys. And oops. And I just want to highlight lastly what still needs to be done and what our work means. So our current study is equilibrium properties of the QCD equation of state, which is very different from an actual system of colliding heavy ions, which are incredibly dynamical. So in order to make direct theory to experiment comparisons, we would need event by event, relativistic, viscous, full BSQ hydroevolution with critical fluctuations and hadronic transport also included. So we're a long ways from there, but that is what would be required for a direct comparison. Okay, that is my talk. Thank you.
Thank you very much for this very nice talk. Questions, please raise your hand while I'm waiting for people to move your hand button. Let me start with a question. You mentioned that when you do the matching of your equation of state to the hadron resonance gas with this hyperbolic tangent function, you have to be careful about preserving continuity for the strangeness and electric charge constraints. So I understand you express everything in terms of mu b by using these constraints to eliminate mu s and mu q, but then that elimination or that relationship gives you different functions of mu s and mu q as a function of mu b in the hadron resonance gas phase and in your lattice QCD attached or adapted phase. So how do you take care of this continuity? How do technically? How do you make sure that?
I understand.
Okay, maybe
okay,
let
so
me turn it around. What did you mean by making sure that you have continuity of the electric charge and strangeness continuity equation?
Okay, so all I meant by that, so these calculations occur entirely separately. So you have a separate code where you do HRG. I think Jamie did this calculation. She probably used the FIST framework, the thermal FIST framework. And within that framework, you can impose those charge conservation constraints. And also, it's important to point out the particle list that you use plays a role here. So the particle list we used for this was the SMASH, the particle list is compatible with the SMASH code. So that is also important to keep in mind. But I think you're right. Like, I don't think those relationships of mu s and mu q as a function of mu b would be conserved as you moved from, the Ising plus lattice description to the HRG description. I'm not sure, just because I didn't work on the HRG part directly. But the way we enforce it is just by separately requiring that the charge conservation conditions are met.
Okay, but it's not completely trivial. Okay, good. I have a chat message that Masood would like to ask a question. Masood, go ahead.
Hi. Thank you for your nice talk, and which I lost parts of it due to this problem.
Well, fortunately, you had 20 people recording it, so.
Yeah, thank you. My question is, it's a very naive question, actually. Is that what parts of the phase diagram is excluded for having critical points? I mean,
are you saying in terms of like the size of the critical region, like how far do you? Okay, let me see. Let me find a nice plot for this. So I think what you're asking is like, how far out do you go until you no longer see critical influence? Is that what you're asking?
No,
like for instance, you wouldn't see any.
Exactly. I mean, what is the region that you can be sure now that there's no critical point?
Is that an experimental question, or is it within the theoretical approach? Are you asking what region is excluded by experiments, or are you asking whether there is an intrinsic self-consistency condition that requires the critical point to lie somewhere and cannot lie somewhere else.
The torchical point of view, I'm asking, because I don't think that.
Okay.
If
so
you
within
can,
our framework, that's not, sorry. Go ahead. I think there's a lag. So when I start talking, you're still talking. Just go ahead.
Yeah, go on, please. No.
Okay, so within our framework, what I can tell you about this is that it's not such a trivial question. You have to actually look at your thermodynamics and see what's going on. One thing that we do would be to look at, let's see, I don't have a good plot for this here. But one thing you could do would be to look at your, a second order derivative will be best for this. So maybe you look at the speed of sound and you can take slices of fixed mu b. And as soon as you don't see the behavior that is introduced by the critical point, which is this dip and peak sort of pattern, that's when you would say, okay, I'm outside the critical region. But I don't think that we have a built-in way of determining that, at least in, and I've worked with things before with this equation of state that required me to know, like, I'm far away enough from the critical point. So usually I would look at chi2, for instance, the second order susceptibility, and look at what those slices of fixed temperature mu b look like.
Thank you.
You're welcome.
I see a hand from Rob Iskowski. Please, Rob, go ahead.
I just have a few brief comments. It was a very nice talk. It's a very impressive work. I just wanted to say, I believe the lattice, can you hear me?
Yes, I can.
Has found evidence for mu to the fourth term in the pressure. Particularly if you plot it not as mu b over t, but as mu quark over 2 pi t, then you find a coefficient that's naturally of order 1. I just have a series of comments. The other, that's just tangential. If you could go to slide 14. Yeah, I don't know why they plot mu b over t. It just doesn't. Should be mu quark over 2 pi t. Is that there's really two important parameters. One is the position of the critical point, and the other is the width. And this is just something of me. Now, you've made an assumption concerning the width, which is fine, because who knows what it is. But it'd be nice if you just rotate that diagram so you could see it in terms of t as well as. You see what I mean? On the right-hand side, there's all this structure, and you can't see it. And in your papers, you never rotate it. You understand what I'm saying?
He wants to look into the valley.
So if you just rotate it 90 degrees clockwise, so you could see better the structure in the T plane. Okay?
Yeah, I think maybe another way to do this, yes, thank you. Thank you for your comments. I was not aware of the recent lattice results, so thank you for pointing that out. But I think a solution for the visualization problem that we have here is we more recently started plotting density plots. So in our kurtosis paper on this, which you watched that talk, Rob, at Fun QCD, we do the density plot so you can see what's actually happening in terms of the structure. But you're right, it's not very easy to see what's happening.
Okay, George.
Hey, so it's actually Jackie. I'm just stealing George's count for a second. But to quick follow up on Rob's question, because I think it was important, is we do have a follow-up paper coming out where we explore the CS squared much more. We just don't have that ready for Debora's talk right now. And in fact, it has a very, very strong correlation to what you would see in terms of high dynamic observables. So we do play around a lot with the width. These are these rho and omegas that Debora talked about. It's rather non-trivial. This goes into what she's doing with machine learning, because there are some regions where, you know, you cut off your rho and omegas in terms of what's causal and stable. So it's a very difficult question that Debora's digging into right now.
All right.
Thank you, Jackie.
All right.
Yeah. No. I just want but just rotate your figures sometimes. It's just I really wanted to grab the Mathematica file and just rotate it by hand. It's not true because, as I'm sure you know, people who do the FRG claim it's a very narrow transition. Now, you may not believe the FRG, that's fine, but it's an important point. But it was a very nice talk. Thank you.
All right,
Thanks.
let me take the opportunity to thank Debora again for this wonderful talk and for leaving us with so much time for discussion without going over time in the program. Thank you very much again. And
Thank you for the great questions.
I'm calling on Farid as the next speaker.